Hi everyone. Welcome to Root Locus Analysis and Design. In this course, you will embark on a journey to understand more details on the root locus concept and its properties to sketch the root locus. The fundamental theory of transfer function and feedback of control system is discussed to relate with the root locus conceptual. In this course, student is expected to be able to analyze complex engineering problem using root locus and frequency domain control systems techniques and also find strategy to solve complex engineering problems. Now, let's dig more deeper about properties of root locus. This is a closed-loop system with unity feedback and it has its own transfer function. The zeros occur at the nominator, ns, while the poles occur at the roots of denominator, ds. Therefore, the characteristics equation of the closed-loop transfer function is derived as h's. Now, in a closed-loop control system, the characteristic equation is extremely important because it tells us about the stability of the system. The standard form of the characteristic equation is 1 plus kg, s, h's equals 0. Now, to understand this equation in the frequency domain, especially for stability analysis, we often express it in polar form. This form emphasizes that for a point on the Nyquist plot to satisfy the characteristic equation, its magnitude must be 1, and its phase angle must be an odd multiple of 180 degrees. To understand where the closed-loop poles of a system will lie as the gain k varies, we need to satisfy two key conditions. Number 1 is the magnitude criterion, and number 2 is the angle criterion. So, what do these criteria mean? Magnitude criterion is essential when determining if a point on the complex S-plane lies on the root locus. The angle criterion determines whether the angle of the open-loop transfer function at a particular point in the complex plane satisfies the condition of being an odd multiple of 180 degrees. Let's summarize the key ideas behind the root locus technique. The root locus shows us how the closed-loop poles of a system move in the complex plane as the gain k increases from 0 to infinity. These criteria come from the characteristic equation, and they help us identify the exact points in the S-plane where poles can exist for different gain values. As the gain k increases, some poles may move toward infinity or settle into new stable or unstable positions, depending on the system. This implies that a complex number will result if a value of s is substituted into the transfer function. Meanwhile, if the angle of the complex number is an odd multiple of 180 degree, that value of s is a system pole for some particular value of k. Therefore, the root locus is the path of the roots of the characteristic equation due to k as k is approaching to infinity. Let's see the example. Based on the given closed-loop transfer function, calculate the angle of g's at the point -2 plus j3. Then, determine whether the point is on the root locus or not. To solve the problem, first let's find all the angles of the vector drawn from the zeros and poles to the point -2 plus j3. Then, all the algebraic sum of angles is calculated and we get 70.55 degree. So, since the algebraic sum of angles is not an odd multiple of 180 degree, therefore the point -2 plus j3 is not a point in the root locus. Now let's see the second example. Based on the given feedback closed-loop system, determine whether the point -3 plus j0 is on the root locus or no. In the point is on the root locus, then find the gain k using the length of vectors. Firstly, let's calculate all the angles of the vector drawn from the zeros and poles of g's to the point of -3 plus j0. Then, sum of all algebraic angles and we get the sum is 180 degree. So, since the sum is an odd multiple of 180 degree, the point -3 plus j0 is a point on the root locus. And since the point -3 plus j0 is on the root locus, we calculated the gain at that point, we get gain value, k of the closed-loop system is 10. So, when we draw the root locus, we are essentially plotting all the values of s that satisfy both the magnitude and angle criteria as the gain k changes from 0 to infinity. These criteria determine the shape and location of the root locus on the complex plane. Now that we've seen how the root locus is related to the closed-loop poles. As a summary, there are two important conditions that must be satisfied by any point on the root locus as we vary the gain k. Thank you everyone for your attention. Hope to see you again in next lecture.